Welcome back to my Calculus Conundrums videos, and we're still talking about applications of derivatives, and in this video we're going to talk about optimization, or otherwise known as max-min applications. Okay, so you can pause the video and read this. I'm just going to go ahead and get straight to the work here. We're going to work with functions that have one independent variable, and you may have to manipulate these functions based on other information you may be given. So I'm going to start you out with some simple examples, and then we'll do some more complex examples. So let's say we want to maximize this function. So we want this function to have a maximum value. Well, I don't know how to maximize this function here because it has two independent variables. It has both x and y in it. But I'm given some more information. I'm given here that the sum of x and y must equal 180. So this is still my primary equation because this is what I want to maximize, but I now have a secondary equation because I know that x plus y equals 180. Now I can actually solve that for y, and I can get that y is equal to 180 minus x. And then so what I can do is I can go to this function and replace y with 180 minus x. And that's what I did down here. So I took x squared times y and I replaced the y with 180 minus x. And then that gives me 180 x squared minus x cubed. And now I can find the maximum of this function by differentiating. So let's take the derivative of this, and we get 360x minus 3x squared. And then of course we set that equal to 0, and then we can find the roots of this by factoring out a 3x, and so the critical numbers of this is actually going to be 0 and 120. Now normally we would say, well, we probably know that 0 is not going to maximize that function, but let's go ahead and pretend like we don't. And let's go ahead and use the second derivative test to test these two critical numbers and see which one gives me the maximum. So the second derivative, take the derivative of this derivative, and I'll have the second derivative, which is 360 minus x. Now if you plug 0 in, then you're going to get the second derivative is greater than 0. So then f of 0 would actually be a minimum. But if we plug 120 in, 360 minus 6 times 120 is going to be a negative number, and so that tells us that f of 120 is a maximum. So now we know the answer that we want is for x is 120, and we can find the y value by just taking the x and plugging it back into my equation for y. Remember, y was 180 minus x, so if we plug 120 in, we get 60. So the two numbers are 120 and 60. And now I didn't really ask you to find the maximum, but if you want to find the maximum, remember the formula was x squared times y. So just multiply the 120 squared and then multiply that by y, and that will actually give you the maximum value. But the x equal 120 and y equal 60 were the numbers that I had asked for. So you can pause the video and read these guidelines. These guidelines tell you what you need to do to solve an optimization problem. But you'll notice that I actually do these as I go through the problem. And so after you've read these guidelines, then go ahead and hit play and continue working the problems. Now I went ahead and put one right here. And right now I'm still working with simple problems. If the price charged for a candy bar is p of x cents, in other words, it's a function of x, then x thousand candy bars will be sold. Okay, so now in a certain city, we've actually identified the price of the candy bar to be 82 cents minus x over 20, and so it says how many candy bars must be sold to maximize revenue. Well, to get revenue, remember, you actually take the number of items you're going to sell here which is x, and then you multiply it by the price. Now, we know the price is this function, 82 minus x over 20, so multiply those two together, and you get 82x minus x squared over 20. And now, if you take the derivative of this, you'll actually get 82x minus x over 10. Okay? And then, remember, the next thing you want to do is set that equal to 0 and solve it. And so if you set that equal to 0 and solve it, you'll get that x equals 820. And of course, remember, it's in thousands, so it's really 820,000. But 820 is what we have. So x must equal 820,000 candy bars to give a maximum. Now, you can verify this easily with the second derivative test. Remember, this right here is the first derivative. Well, the second derivative, this is 82 minus 1/10 x. Well, if I took the second derivative, this would disappear, and then the derivative of minus 1/10 x would be minus 1/10. So the second derivative would actually be negative. So the second derivative would be negative no matter what I plug in, so obviously it's going to be negative when I plug 820 in. So therefore, since it's a negative, then I know that the revenue at 820 is actually a maximum. Now, it did not ask for the maximum, it just asked for how many candy bars, and we know it's 820,000. But if you want to calculate the maximum, go ahead and plug 820 into the revenue function and solve it, and then that'll show you the maximum revenue. Alright, now on the rest of these, I won't ask you to show whether it actually truly is a maximum or a minimum, but you really should check that just to make sure. Okay, here's another easy one here. This function is an approximation to the number of salmon swimming upstream to spawn, where x represents the water temperature in Celsius. And it says find the temperature that produces the maximum number of salmon. So on this one, we don't really have to fool with a secondary equation because we have everything we need in this equation here. So take the derivative of this equation here, or this function, and I get minus 3x squared plus 12x plus 288, and then set it equal to 0. So just take the derivative, set it equal to 0, and then you can factor a negative 3 out, and you get negative 3 times x squared minus 4x minus 96. And then factor that into x minus 12 and x plus 8, and then set these two factors equal to 0, and you get x equal 12 or x equal negative 8. Now, one giveaway here for the negative 8 is it says the temperature, we're only supposed to use the domain from 4 to 20, so negative 8, we're not allowed to use it anyway. So the temperature that maximizes the number of salmon must be 12 degrees Celsius. Okay, I assume at negative 8 degrees it minimizes the number of salmon because it probably freezes them. Alright, let's take a look at this problem. A box is made from a 20 by 20 piece of cardboard, and squares are cut from each corner, and the sides are turned up to create the box. Express the volume of the box as a function of the x by x cutouts, then maximize the volume based on x. Okay, so let me insert some things for you here. Okay, so what I wanted to show you is that each of these corners that we cut out are just x by x corners. And so I'm going to cut out a corner here that's x by x. I'm going to cut out a corner here that's x by x. Now, all the sides are going to be the same for the base of the box, but let me show you the base of the box. The base of the box, see if I can make this work here, is actually going to look like this. So that's actually going to be the base of the box. So let's talk about the dimensions of the base of that box. Alright, you know it's 20 all the way across from here to here. And then so the dimension from here to here would simply be 20 minus 2x, because you'd say 20 minus this x and then minus this x. So you'd have 20 minus 2x. And so actually that would be the dimensions for each side. It would be 20 minus 2x. And then the height of the box, since we're going to turn this up, the height of the box would just be x units. So now we know that the length is 20 minus 2x, the width is 20 minus 2x, and the height is x. So now if we multiply all these together, 20 minus 2x times 20 minus 2x is 400 minus 80x plus 4x squared. And then we have to multiply all that by x, so we get the volume of the box is 4x cubed minus 80x squared plus 400x. So now I have my volume written as a function of x. Now I can take the derivative of that, so the derivative of that would just be 12x squared minus 160x plus 400. And so remember, what I want to do is I want to set that derivative equal to 0. Now, you can actually solve this by using the quadratic formula or factoring. And if you factor this and solve it, you'll get two answers. You'll get x equals 10 or x equals 3 1/3. Now, the answer can't be 10, because if the answer was 10, think about it. If you let x be 10, put 10 in here for this and see what happens. You'd have 20 minus 2 times 10, that would be 20 minus 20. You'd have 0 dimensions. So there wouldn't even be there. Actually, if you cut out 10 by 10 squares out of each corner, you wouldn't have anything left for the box. So the only answer that works is 3 1/3. So the answer would be 3 1/3. And that's, these types of problems are used quite a bit in manufacturing. And I do have some more examples, but I'm going to put those on the next video.